Okay, here is a practical lesson on the decay of dice. Now, it's going to be used with the topic of radioactivity, and essentially what we're looking at is we're looking at whether we can use a dice to model how radioactive atoms decay. So with that in mind, let's just imagine to ourselves we have a radioactive atom. It will give out radiation in the form of alpha, beta, and gamma. Something to bear in mind would be that if we had a smaller atom, it gives out alpha, beta, and gamma, well, depending upon the radioactive isotope, but a smaller amount. So the larger the atom, the greater the amount of radiation given out, smaller the atom, less amount. Now, what we have here is we have a collection of atoms inside, individual atoms inside this sample, and we're going to model each one of those as a dice, as a die. If we roll the die, there is a probability of it hitting a certain number. In actual fact, the probability of the dice is a sixth to land on any one of the numbers. And with radioactive decay, the chance of one of these atoms decaying is governed by probability and probability alone. There is a probability which is isotope dependent as to whether that decays or not decays. And when it decays, of course, it produces an alpha, beta, or gamma, or many of them, or some of them. So what we're going to do is we're going to imagine to ourselves that we have a radioactive atom of dice, and we are going to roll these dice, and the number that land on one, let's just say for a number 1, will be the number that have decayed. So very simply, we'll take the dice, we'll roll it, and the number of ones that we find, 1 for instance, has now decayed, and the rest remain inside the atom, because the rest were not ones. And then we'll take the sample again, and we'll roll it, and those that roll as ones will move across the decay, and those that haven't will leave in the atom. Okay, so with that in mind, let's just bring up our table of results. So, what do we need here? What's our independent variable? Well, we want the number of rolls. We're going to look for the number that decay. And we're going to look at the number remaining. Of course, what you'll be given is many, many more than this. You're going to be given something in the order of 150 odd dice. We're going to roll all of those, and then we're going to see what happens after 1, 2, 3, 4, 5, etc., etc. The reason why I use 0 is because we want, of course, to know the number initially. 197, for instance. And therefore, we can work out how many decay. So, once you get that, and you roll away, count them all up, and we'll see what the answers are. I'll quickly pause and then get the results, and then we'll talk about them. Okay, slightly different change of view here, but this is the number of rolls that we've had. This is the number of decays, i.e. the number of these radioactive dice that have fallen on a 1 each time, and therefore what remained from our 87 that we started with. And you'll probably notice that these down here, you're expecting about a sixth to have decayed each time. Because remember, the probability of getting a 1 on the dice is about a sixth. So if I had 87 to start with, then my first point here, I would expect to be 87 over 6. And it's about right. But as you come down, suddenly you get these fluctuations. There's a fluctuation there. Here's a fluctuation here. You're expecting this number to decrease all the time. the more that we use, the more starting point, the more number that we had at the starting point, the more this is likely to show a nice predictive pattern as you get in radioactive decay. Next stage, we need to plot some graphs. We need to plot the number of rolls, because that's obviously our independent variable, number of rolls against the number remaining. And what we should notice is something that comes out like a nice smooth curve. In actual fact, this is an exponential curve, something I'll explain in just a moment. And then as well, what we ought to do is we ought to plot the number decaying against the number of rolls again, because that too is a nice decreasing curve. Now this one's interesting because though this one gives a nice neater result, it's rare to be able to stare into an atom and work out the number remaining. Often you're looking at what's given out. So if you imagine to yourself, this is looking at the number that are inside. This one's looking at the amount that's given out. But they both follow the same laws predictively. Once we've done that, one final stage, and that is you're going to look for whatever any starting point we like, say n, and then you're going to look for the point which is n over 2. And you're going to find out this number of rolls, because that should give you an analogy to the half rolls. In other words, the number of rolls needed in order for the initial starting number to decrease by half. And the interesting thing you'll find is it doesn't matter where you start that. If you go to half, you will notice that these are identical, those number of rolls, or depending on the size and the fluctuations you get, because this is a random process, these should be the same, because this is exponential. So it doesn't matter where you start, but the number given out will be proportional to that which you started with. Okay, so once we've got these results, plot, find out the half number of rolls, and I think it's something like 4.2 rolls-ish. Okay, there we go.